Today we are going to revise our second chapter titled Electric Potential and Capacitance. Okay, it's not that the concepts or things that we learned in the first chapter are irrelevant here. We are still pretty much talking about electrostatics, charges that don't move, but okay, the ideas that we develop here, they will be useful in our later parts of electricity and magnetism, and you actually know that. Okay, so let us begin with the concept of work done by a force. Okay, first one, and the second one is conservative force. Okay, so what is work done by a force? Work done by a force is a scalar quantity. Okay, work done by a force is a scalar quantity, and it is defined as the dot product of the force and the displacement. Okay, I'm now writing displacement as L bar. Okay, so L bar refers to the displacement vector. Okay, so how do you define displacement vector? Can anybody tell me that? Suppose I'm here, and suppose by following some path I go here. So what will be my displacement vector?
The shortest distance, shortest line joining the two.
Yes, exactly. So the displacement vector is given by joining my final position to my initial position, that is displacement. Okay, so this is my displacement vector. Okay, so work done is the dot product of the two, and if either the force is not constant or if the force changes with displacement, in short, then we must consider the integration. In that case, we write it as f bar dot dl bar. Okay, let's say from A to B. Okay, that is work done. Now, there are two categories of forces. Some are conservative, some are non-conservative. So, do you recall the distinction between a conservative force and a non-conservative force? Yes. What is it?
Conservative force does depend on the path taken. It doesn't depend on the path taken.
Yes. Yes.
Non-conservative forces depend on the path taken.
Yes. Okay. So let me write down examples of conservative forces. Examples of conservative forces are gravity, then Coulomb force, okay, which is part of Lorentz force, okay, and so on. These are conservative forces. Okay, these are conservative forces, and friction and viscous force, okay, or air drag. These are non-conservative forces. Okay, so 2 points are there. First point about conservative forces is that work done is path independent. Work done is path independent. Okay, work done is path independent, and the second important point is this work done is actually stored in the system in the form of potential energy. Work done gets stored in the form of potential energy in the system. Okay, so it's actually negative of that, because if I raise an object from this point to this point by height h, the displacement is in this direction. Okay, so L bar is in this direction, whereas the gravitational force is acting in this direction. Okay, so the work done by the gravitational force is negative, because the angle between the force vector and the displacement vector is 180 degrees. So cos 180 is -1. correct? But we define the potential energy as the negative of the work done by the force, by the conservative force. Okay, but there are 2 points. Every conservative force is always associated with a potential and a potential energy. Is that clear? Okay, and the importance is that the Coulomb force that we are going to discuss in this chapter, okay, is actually a conservative force. Okay, and therefore we can associate with the Coulomb force a potential or potential energy, and that's what we are going to call, or we call, electric potential or electric potential energy. Alright, let's now head towards the definition of electrical potential energy. So if you remember, this is the diagram from our textbook, in which we have a point charge q at origin. Okay, so this charge is going to create its own electric field, and we assume that there is a small test charge here. Okay, this is our test charge, which is being moved gradually without acceleration from position R to position B. Okay, so what is going to happen to Q? Q will experience an increasing repulsive Coulomb force. Correct? It will experience an increasingly repulsive Coulomb force. Why? Because it is getting closer to Q. As it gets closer to Q, because both are positive, we have assumed that both are positive. Okay, what does that mean? That means we have to push this Q from R to P against the electric or electrostatic repulsion of capital Q. So the work that we do as an external agent is stored in the form of potential energy in the charge. Okay, so work done by electric force, okay, work done by F electric, okay, what will it be? The work done by F electric will be integral from R to P. Now please note that when I say R and P here, I don't mean these letters R and P, or I don't even mean the points. By that I mean the position vectors of R and P. Okay, F electric dot dl bar. Okay, this is the work done by F electric. But how do we define the electrical potential energy? Electrical potential energy U, as our charge goes from R to P, is defined as the negative of this. Okay, the negative of the work that is done by F electric. Okay, because something else is pushing that charge. It is not going to go on its own towards Q, because already they are repulsive. Is that clear? So it is always the negative of the work done by the electric force is the electrical potential energy, and actually it is the change in the potential energy. So it is UP minus UR. Okay, it is the change in the potential energy. We are always interested in the change in the potential energy and not the absolute value of the potential energy. Okay, we are interested not in the absolute value, of potential energy, but in the change. Okay, change in P. So we are always interested in delta U, so we can choose any convenient location and assign potential energy to be 0 there. Okay, the chosen notation is what? The chosen location is what? The chosen location is U infinity. At infinity we say the potential energy is 0. This is what we assume. Okay, for this particular situation. Have you understood this? Okay. Now we define electric potential. Okay, now we define electric potential. How do we define it? Electric potential is defined as the work done by external force Okay, in moving a charge, in moving a point charge rather, okay, let's say charge, in moving a charge from infinity, okay, from infinity to a location. Okay, so see, this is actually definition of electrical potential energy. So how do we define electric potential energy? So I say moving a unit charge. Okay, electric potential is the work done by external force in moving a unit charge from infinity to a specific location. So electric potential V is actually what? Work done per unit charge. Okay, so that allows us to write the definition of 1 volt, okay, to be 1 joule per coulomb. Okay, so the potential of 1 volt refers to the work done by an external force of equal to 1 joule, okay, when you move a charge of 1 coulomb from infinity to a respective location. Okay, so I hope you understand what electrical potential is or what electric potential is. It is actually the work done in moving a unit charge from infinity to some specific location. This is called as electric potential. Okay, so you may write it as U by Q, and therefore delta V, that is potential difference, is delta U, change in potential energy per unit charge. You may write change in potential energy as Q delta V. Is that clear? Okay. Now there is one more point. In the analysis of capacitors, okay, in the analysis of capacitors, we'll come to that later, but I just want to mention one thing here. When we say that the capacitance C is Q by V, okay, here by V we mean delta V. Okay, what is delta V here? It is the potential difference between the plates of the capacitor. That delta V is what we are referring to, and we often call this potential difference. We often call it potential difference. There is an analogous quantity called EMF, okay, which we have studied. Because it is not part of this chapter, we will not study it right here, but EMF and potential difference are closely related to each other. And there is one more quantity that appears there, that is electrical resistance. But as we are talking about static situations, there is no current, so we will not talk about EMF. But I hope you understand the potential difference. Okay, electric potential difference. Alright. Number 4, electric potential due to point charge. Okay, electric potential due to point charge. The definition remains the same. Okay, the definition remains the same, but now we say that the electric field in which our charge is moving, unit charge is moving, is created by a point charge. Okay, is created by a point charge which is situated at the origin. Well, we actually bring in the coordinate system later. Okay, first we specify where are our charges, and then we introduce the coordinate system as per our convenience. Okay, so what is electric potential due to a point charge? We can very easily find the electric potential, okay, by applying the definition of electrical potential energy and dividing it by the charge that we are moving. So I'm not going to explain the derivation here, but this expression here refers to that formula which I will be using to calculate electric potential due to a point charge. Okay, and what will this tell me? This will basically tell me that if my charge is at P, the work that I need to do to get it from infinity to this location is Q upon 4 pi epsilon naught R into the value of the charge that I'm bringing from infinity to this point, because this is potential. This potential refers to work done per unit charge. Work done per unit charge. Okay, so let me write a few points here. Point 1. VR equal to Q by 4 pi epsilon naught R applies only to a point charge. Okay, first. Yesterday we talked about the electric fields in using Gauss law. Okay, we talked about an infinitely long linear charge distribution, then surface charge distribution, and also a sphere. Okay, a spherical shell. Okay, we could calculate electric fields due to those because they were very simple symmetric charge distributions. But here we are not talking about charge distribution, continuous charge distribution. We are just talking about a single point charge. Okay, so VR is equal to Q upon 4 pi epsilon naught R. This applies only to a point charge and not to a continuous charge distribution. Okay, not to a continuous charge distribution. Point number 2. If a charge small q, okay, if a charge q is brought from infinity to p, okay, which is whose position vector is r bar, let's say, where our capital Q is at origin, then work done, okay, by external force, that will be the potential energy acquired. Okay, potential energy acquired. Okay, what will it be? It will be Q into VR, where VR refers to this formula. आता हा फॉर्म्युला हा इन जनरल सगळीकडे ॲप्लिकेबल आहे. वर्क डन इज Q into VR, कारण तोच आपण इथे लिहिला आहे, राईट. इररिस्पेक्टिव्ह ऑफ whether it is due the field that is there, that exists in the space, is because of a point charge or a distribution of charges or even continuous distribution. Okay, but this formula, which one, the one that I'm highlighting in the red color, this applies only to a point charge. Okay, that is electric potential due to point charge. Okay, fifth point I just want to add here. Yesterday we talked about electric field due to a point charge, and the expression was 1 upon 4 pi epsilon naught q divided by r square in magnitude. This was the expression for electric field. Let me remind you that this is due to point charge. Okay, this is due to point charge. Now what expression did we see for potential? 1 upon 4 pi epsilon naught q divided by r, right? This is the expression that we saw here. So E varies inversely with square of r, magnitude of electric field, and potential, which is already a scalar quantity, varies inversely with the first power of r. Okay, so you remember this relationship, proportionality relationship between E and R and V and R. Okay, they might ask you this in multiple choice questions. There are some other situations here, how potential drops or how electric field's magnitude drops in the case of electric dipole. Okay, we have talked about electric field of a dipole yesterday in our revision of the first chapter, and now we talk about potential due to a dipole. I will not explain again what a dipole is and all that stuff, but let me remind you that P bar is electric dipole moment. Okay, P bar is electric dipole moment. Okay, in magnitude it is equal to magnitude of any one of the charges into the distance between them. Okay, and the direction is from negative q to positive q. At P we know how to find the electric field, but now let's find electric potential due to this dipole. Okay, the procedure is simple. The actual value potential at this particular point will be given by 1 upon 4 pi epsilon naught, number 1, q divided by r1 plus negative q divided by r2. So I'm basically using superposition here. Okay, and because these are 2 point charges, I can make I can apply the same formula twice. Q upon 4 pi epsilon naught r. But after this, okay, we make some modifications in the derivation. If you see, we use the cosine rule of triangle, then we use binomial expansion, and then at the end we say that if the point P is at such a distance from the center of the dipole which is very much greater than the length of the dipole itself, in that case the potential at that point, okay, is P bar dot r cap, where r cap is the unit vector in a direction which is from the point the center of the dipole to the point where you want to find the electric potential, divided by 4 pi epsilon naught r squared. Okay, so potential does not always vary inversely with r. It also varies inversely with 1 upon r squared for dipole. So this can also be a multiple choice question. How does potential change or vary with r? If in case of a dipole. Okay, so for dipole it varies inversely with square of the distance, whereas for a single charge, a point charge, it varies inversely with the first power of r. Is that clear? Okay, is that clear? Yes. Okay. Now, extending our discussion on the potential due to a dipole, we choose specific locations. In particular, if I choose the equatorial plane like this, then because r cap here is perpendicular to p bar, the electric potential here will be 0. Okay, if electric potential will be 0 on equatorial plane, and later we are going to call this, or rather we have called this in our regular lecture, what? An equipotential surface. Okay, equipotential surface. That means the locus of points where the value of the potential in a field is same. Alright. Next, potential due to a system of charges. Again we apply the superposition here, and yesterday we have seen that superposition in terms when we applied to vectors or the electric fields is not just the vector law of addition. It also refers to the fact that if you have more charges present, let's say we just consider q1 and q2, or even just q1, so the potential or electric field at p due to q1 is unaffected by the presence of the other charges, and same thing applies to every other charge. Okay, in that context we apply superposition here as well. So the potential at p due to q1 will be still the same irrespective of whether the other charges are present in the vicinity of q1 and p or not. Okay, so we apply the same formula here and say that the potential at p is given by summation j going from 1 to n. Here it is shown for just 5 charges, but you can have as many charges as you want. So Vp is summation as j goes from 1 to n qj divided by 4 pi epsilon naught rj. Well, I may write it as rjp, but I hope you understand what that means. Okay, let me write it as rjp. Okay, that is potential due to a system of charges. Have you understood this? Oh, just okay. Yeah, okay. Okay. Acha. So we had completed a potential due to system of charges, and now let us head towards potential inside and outside a charged spherical shell. There are two important results here. Result number 1 is that potential drops linearly, or potential drops inversely with the distance of the point from the center of that spherical shell, and this is not a surprise, because you know that the electric field, okay, outside the charged, uniformly charged surface, okay, spherical shell, that is given by 4 pi r squared sigma upon 4 pi r squared epsilon. Okay, if you remember this, the numerator here is actually the total charge on the surface. You know that. Okay, surface charge density into total surface area. So this is as good as saying that there is a point charge situated at the center of this shell shown in the blue color, assumed very thin, and that point charge is creating its own electric field. Okay, so outside it is just like a point charge situated at the center. Okay, so this expression here that you see is basically the same. Okay, Q divided by R, where Q is the total charge. Okay, so this small q is the total charge in this case. This is the textbook notation. This refers to Q, the total charge. Q refers to total charge on the shell, or I would say net charge. Net charge on the shell. Net charge on the shell. Okay, so there, because electric field has this expression, we can expect the potential also to have the similar expression, and yes, that's indeed true. So this potential is the same expression that you see here. Okay, where is it? Capital Q upon 4 pi epsilon naught. The only difference is here they have called it capital Q because it is a point charge, and here they are calling it small q because it is behaving like a point charge kept at the center, magnitude equal to 4 pi r squared sigma. R is the radius. Okay, now if you recall or if you remember, electric field inside the thin spherical shell is 0. Okay, electric field inside is 0 because the Gaussian surface, if you take any surface, any Gaussian surface inside the shell, it doesn't bound any charge, it doesn't enclose any charge. So the electric field is 0. And in this chapter later on we had seen the derivative relationship that exists between electric field and electric potential. Okay, so if electric field is 0, then the electric potential is a constant. So in this case it is indeed a constant, and how much is it? That electric potential is equal to the value that it has on its surface. You can see that this is small r here, that small r is replaced by this capital R. Capital R refers to the radius of the thin spherical shell. Okay, so by this we mean at the surface of the shell and in its interior, electric potential is constant, or electric potential has the same value. Okay, has the same value, so, and that is equal to the surface, the electric potential at its surface. Is that clear? So if I were to draw a small graph here, if I were to draw a graph of variation of potential, let me draw it here. If I were to draw a graph of variation of electric potential with R, okay, it would look something like this at R, capital R, and then after that it will drop like this, and it will continue to go closer and closer to the horizontal axis. Okay, that is the graph of electric potential against distance. Okay, but this is only to spherical shell. Fine. Ninth, equipotential surfaces. What do I mean by equipotential surfaces? The definition of equipotential surfaces is that they are locus of points, or set of points, I would say. Mathematical term is locus. Set of points, you can understand that it's a locus of locations in space where potential V has the same value. Electric potential V has same value. Okay, has same value. In the case of this particular geometry, the equipotential surfaces are spheres of radius r. Okay, because everywhere the potential is the same due to symmetry. Okay, so that is an example of equipotential surface. Shown here are 4 different possibilities in which there are 4 equipotential surfaces shown: V1, V2, V3 and V4. What do we find? Electric field is always perpendicular to equipotential surface. Okay, electric field is always perpendicular to equipotential surface, and if you look at the textbook figure telling you this, that equipotential surfaces and electric field are perpendicular to each other, you can connect this to something that we have studied very recently in wave optics. and that is c bar, or the direction of propagation of light, is always perpendicular to wavefronts. Just an analogy. Okay, if you, in fact, if you look at the diagram which your textbook it gives you for planar wavefronts, and if you look at the diagram that you see here for planar equipotential surfaces, they look exactly the same. Okay, just to give you an idea. Okay, now what is the significance of equipotential surface? Okay, what is the significance of equipotential surface? Because electric force is conservative, the work done by it will be path independent. So if you move your charge on any equipotential surface, the work done is zero. Okay, that's first. If you एक मिनट, तो ऑफलाइन एनआर एस का ऑनलाइन एनआर एस फिजिक्स का ठीक है, संवाद आ रहा है एकच मिनिट
कोणीच नाही, फक्त एक त्यामध्ये रिलच शिकवलं, रेकॉर्डिंग केलं, कोणीच नाही.
तुमची टर्मिनल कधी आलं? तुमची झाली का?
हो, युनिट टेस्ट क्वेश्चन बँक मिळाली तुला केमिस्ट्रीची काही, फिजिक्सची पण आली आहे आता.
पाठवा. Yeah, okay. So we were discussing the motion of a charge along equipotential surface, work done is zero. Okay, because there is no change in potential. Remember, work done is q delta v. Now if equipotential surface is there, then delta v will be zero, so for this work done will be zero. Same thing applies if you let your charge leave an equipotential surface but again return to the same equipotential surface. Okay, so work 1 is 0 and work done along the second path is also 0. Okay, because it is path independent, right? Because it is path independent, and the other consequence of this is that because the work done is path independent, because it is a conservative force, the electric force is a conservative force. If you follow two different paths which start at the same equipotential surface and which end at the same equipotential surface, in this case V1 and V2, then equal work is done. So W3, okay, W3 and W4, they both are same. W3 and W4, they both are same. Why? Because both of them will be equal to Q times V2 minus V1. Okay, fourth is V2 minus V1 into Q, and work along third one is also Q into V2 minus V1. Have you understood this? Okay. Acha, I had shown you these figures when we had discussed this in our regular lectures. If the electric field is uniform, okay, then the equipotential surfaces are planes. You also had the mathematical treatment of this surface called plane in maths, but in your batch, for your batch, it was omitted, right? In maths, planes. Okay. Now, also if you have a point charge, be it a positive point charge or a negative point charge, and it is isolated, then the equipotential surfaces will be spheres, concentric spheres. Okay, equipotential surfaces will be concentric spheres, and as expected, the electric field lines are normal to these. So if radii represent electric field lines, then the sphere represents equipotential surface. Okay, and here there is no question. Okay, you can clearly see that they are perpendicular. Okay, now for a dipole, equipotential surfaces are complicated. to visualize in 3 dimensions. They are approximately spherical near the positive and near the negative charge of the dipole, but there is one prominent equipotential surface of a dipole, and that is this equatorial plane. Okay, the equatorial plane of any electric dipole is an equipotential surface, and it is rather the only flat equipotential surface that a dipole has. Okay, every other equipotential surface will be curved. We don't have its mathematical treatment, but keep in mind that electric field, no matter in what situation, will always be normal to the equipotential surfaces. Okay, the field is always normal to equipotential surfaces. Is that clear? Okay. Okay. Next is relation between electric field and electric potential. Okay. Now, the most general form of the relationship between electric field and electric potential will be introduced to you in engineering mathematics, and that goes something like this. Electric field is negative of gradient of V. Okay, gradient of V involves derivatives, partial derivatives we call them. So in this case, we just say that electric field's magnitude, or okay, can say electric field, so to speak, is equal to electric field magnitude is known upon, to make things simple, it is the potential difference that would change. Okay, the potential that would change, the difference in the potential divided by the distance. Okay, the distance. So for example, if you are here and let's say you go to this point, so this will be the distance between the 2 points will be delta L mod. Okay, and if the potential changes as you go from this point to this point by delta V, then you say that the electric field here is in magnitude delta V by delta L. Okay, electric field there is delta V by delta L. So this relationship between electric field and electric potential gives us an alternate SI unit of electric field. Okay, we know that the electric field is measured in Newton per coulomb because it is force per unit charge. Yes, you know that. But we can also talk about 1 volt per meter. Okay, 1 volt per meter. Okay, so both of these are equivalent units. So 1 Newton per coulomb of field is actually 1 volt per meter of field. So if the potential difference is 1 volt when you go 1 meter, then you can say that the electric field there is 1 Newton per coulomb. Got that? काय? इलेक्ट्रिक फील्डचं डेफिनेशन नुसार काय आहे? इज इट नॉट फोर्स पर युनिट चार्ज? व्हॉट इज द एसआय युनिट ऑफ फोर्स? व्हॉट इज द एसआय युनिट ऑफ चार्ज? हां मग I don't remember what I said. Precise statement. Okay, what I was telling you was electric field and electric potential are the vector and the scalar facets of one and the same phenomenon, and that helps us understand how charges interact with each other when they don't move. Okay, how forces, how much force does one charge exerts on other charge. Okay, so in electric, if you want to talk about the same interaction through electric fields, then vectors will be involved, complicated calculations will arise. If we talk about scalars like electric potential and work done, the analysis will get much simpler. It depends on what you want. Okay. Acha. Now if you want me to explain this, the electric, okay, we say that the electric field is 1 Newton per coulomb when we take 2 points separated by 1 meter. If you find that the potential difference between them is 1 volt, you can say that there is a field of 1 Newton per coulomb in between these two locations, assumed uniform. Yeah, exactly. The point is, when you talk about electric field, you talk about a specific location. But when you talk about potential difference, you talk about 2 locations. Okay, and that's why you need derivatives here. Okay, so त्यांचा actual relationship असा आहे. It's negative of partial derivative of v with respect to x I cap. पण तुम्हाला आता पार्शियल डेरिव्हेटिव्ह म्हणजे काय तेच माहीत नाही आहे त्याच्यामुळे but yes they are actually a derivative but v depends on multiple variables, not just x but it also depends on y and z. Okay, anyways, so that's e bar and v. So yes, so electric field is the steepest, or electric field changes in a direction where potential difference changes the quickest. Okay, let me give you an analogy. Look here. Imagine on a map you have these contour lines. Okay, suppose these are contour lines. Now what are contour lines? Contour lines are those lines shown on the map which actually correspond to three-dimensional curves, okay, so to speak, where every point has the same value of height from the sea surface level, correct, or elevation. So elevation. So that elevation in the context of a map is what potential is in the context of electrostatics. So the contour lines refer to equipotential surfaces. Now if I ask you, oh, just tell me the shortest distance which I can cover or which I should cover to reach the ground from the summit. Okay, then what you would do is you would start walking normally. So मग तू प्रत्येकेला करत गेलास तर तुला नॉर्मल असं करत करत जावं लागेल पुढे. So that will be, yeah, exactly, that will be the direction of electric field, and that by not surprisingly that also means the steepest path that you will be taking. Okay, and you avoid that. That's why we when we descend we always go in the zigzag manner, because we don't want to feel the gradient. Okay, त्याला actually gradient म्हणतात त्याचं कारणच ते. It is a mathematical operator, gradient. Electric field decreases okay, electric field, okay, एक minute. We will take the situation of a point charge just to put my point. Okay, suppose हा माझा point charge आहे, बरोबर. आता ह्याचे जे इक्विपोटेन्शियल सर्फेसेस असणार आहेत ते कॉन्सेंट्रिक स्फिअर्स असणार आहेत, बरोबर. ओके, आता तू मला सांग इथे इलेक्ट्रिक फील्डचं जे डिरेक्शन आहे ते कसं आहे, तर नॉर्मल आहे, रेडियली आउटवर्ड, करेक्ट. Now you tell me, let me call this as V1 and let me call this as V2. Okay, and suppose the charge is positive. So is V1 greater or V2 greater? No, V1 is greater than V2, right? Because V varies inversely with R. Okay, so V1 is greater than V2. Now if I ask you to tell me the electric field at this point and electric field at any other point in magnitude, okay, where will you find the magnitude to be greater? Is it at A or is it at B? Exactly. Now you apply this to the statement that you made and check. So the potential is decreasing radially outward, and so is the strength of the electric field. If you want to talk about the direction of the electric field, okay, or the direction of electric field line, so to speak, electric field line, then that line will be normal to the equipotential surfaces, and that line will follow the path where the potential is decreasing. कळलं? या म्हणजे जर तू इलेक्ट्रिक फील्ड लाईन तुझी अशी आहे आणि जर तू त्याला नॉर्मल असे सरफेसेस काढले तर तुझ्या लक्षात येईल की पोटेन्शियल कमी कमी होत गेले या डायरेक्शन. दॅट्स अ कन्क्लुजन दॅट यू हॅव टू ड्रॉ. ओके फाईन. Okay, so yeah, that's the significance of the negative sign. Alright, next point is potential energy of a system of charges. So this refers to energy stored in the system which went in during the assembly of charges. Okay, so when these charges were at infinity charges, and when they were brought to their positions, okay, well, there will be some energy that goes in, because see, for a single charge there is no energy because there is no field, there is no force, so there is no work, so there is no potential energy. But the moment you start assembling the second charge from infinity and put it here, then this system will acquire an energy. Okay, this system will acquire an energy which depends on R12, Q1 and Q2. So how can you tell me the formula for the electric potential energy in the first case? 1 upon 4 pi epsilon naught Q1 Q2 divided by R12. That's the formula. Okay, you can apply it either way. If you want to talk about potential due to Q2, then don't write Q1. If you want to talk about potential due to Q1, don't write Q2. Okay, but nonetheless the expression matches. Okay, so this is Q. Now if you remember, while discussing atomic structure of hydrogen atom, we said that the potential energy is how much was that? Negative 13.6 electron volt, right? Okay, so we had assumed that the proton is here and the electron was brought from infinity to its first orbit. And how much energy was released? Okay, negative 13.6. कारण काय हे अट्रॅक्टिव्ह आहे. ओके, अपोजिट चार्जेस अट्रॅक्टिव्ह म्हणजे ते चार्जेस ब्रेक करण्यासाठी तो बॉन्ड वेल नॉट एक्झॅक्टली बॉन्ड बट दिस टू ब्रेक द स्ट्रक्चर अँड टू आयसोलेट द प्रोटॉन फ्रॉम अँड द इलेक्ट्रॉन वी मस्ट सप्लाय अन एनर्जी at least equal to 13.6 electron volt. There we use the concept of potential energy. Got it? Okay, Ritika, can you tell us what will be the potential energy for a system of 3 charges here? Well, you have to consider pairwise because these are scalar quantities, right? Correct. R23 plus Q3 Q1 R13 or R31, you can write it anyway. Okay, so in general if you have n charges, then in your potential energy term there will be nc2 terms. Okay, nc2 is how much? n into n minus 1 by 2 terms. Okay, so if you have 3 charges then 3 terms, 3 into 3 minus 1 2 by 2. हे NCR चा फॉर्म्युला तुम्हाला 11वीत झाला, right? So those many terms will be there. So if you have an assembly of 30 charges, then how many such terms will be there? 15 into 29. Okay, fine. Okay, now there is one more situation. What we say is even before the charge Q1 comes from infinity and takes its place, there already exists electric field in that region. We don't specify the sources of that electric field, but we just say that okay, let this be the case. So we now discuss potential energy of a charge or a system of charges in external electric field. Okay, so we don't specify this. Okay, the source of this field is not specified. Okay, the source of this field is unspecified. Okay, is unspecified. Okay, now let us again consider a dipole like structure. Suppose charge Q1 comes from infinity and takes its position here. Okay. Now previously electric field was absent, so charge q1 could roam anywhere. Okay, it could roam anywhere in the space, just like a child on a ground. It can go anywhere. So just like that, this charge could go anywhere. Okay, without any force. But in this case, there already is electric field. Okay, so due to this external electric field, there will be potential. Okay, there will be potential, and suppose the charge q1 takes this position, so we must consider the potential energy. Okay, when this charge q1 interacts with the external electric field, so that is given by q1 into v r1 bar. Now this v here, this v is not due to other charges. This v is due to E external. Please note that. So q1 into v, well, agreed, that's the right formula. But in this case, this v is not due to other charges, but it is actually due to the external electric field whose source is unspecified. Similarly, we must multiply the charge q2 by the potential at the point where the q2 is situated. Okay, and after this there will be one more term, okay, which will come because of the charges also experiencing each other's electric field, which is different from the external electric field. So it will be q1 q2 upon 4 pi epsilon naught r12. Now don't think that because we have used r1 bar and r2 bar, v will be a vector quantity in this case. No, it's still a scalar quantity. Okay, by r1 bar and r2 bar I mean the position vectors of q1 and q2. Okay, so suppose this is the origin. The position vector of point q1 is this, and the position vector of point q2 is this. Okay, so this is my r2 bar, this is my r1 bar. Why do we need this? Because there is an external electric field. Is that clear? So if we have three such charges, then how many terms will be there? 6 terms will be there. 3 potential energy terms due to charges, and 3 potential energy terms due to electric field external. Okay, because there are 3 charges. And similarly, you can develop expressions for more number of charges present in an external electric field. Okay, that takes us to potential energy involving rotations. Okay, potential energy involving rotations of system. So we talk about the simplest of all, electric potential energy of a dipole which is placed in external electric field. Here we assume that electric field is uniform. What do we assume? The assumption is that the electric field is uniform. Otherwise we will be required to perform integration. Okay. Now what will this dipole try to achieve when left in an external electric field? Okay, in what position will it stabilize itself? It will stabilize itself in such a position where the forces acting on the positive and the negative charges become collinear. Okay, so force on this will be QE bar in this direction. Okay, and the force on this will be QE bar in this direction. Correct? So these two forces will actually act on this, and because electric field is constant, the force will also be constant, and this will cause this dipole, okay, to rotate clockwise. Okay, can you visualize this rotation about the center? Got that? Okay, okay. So there will be torque, okay, there will be torque tau bar given by P bar cross E bar, and this torque will do some work because of the rotational displacement or angular displacement. We call it angular displacement, and the work done, okay, can calculate it by integrating tau. I will not do that now, but let's say theta naught to theta. If you do that, because integral of sine is negative cos, you get the expression for the work done as PE. Now see, this is actually the integration of PE sine theta. Okay, this is an integration of that. So it is cos theta naught minus cos theta 1, where theta naught is the initial position and theta 1 is the final position. So never forget this expression. We have a similar expression even for a magnetic dipole like a bar magnet or a current carrying loop when placed in external uniform magnetic field. Okay, and there the way we write it is mb cos theta naught minus cos theta 1. Okay, now this work done is stored in the form of electric potential energy, but as I said, we are always interested in change in the potential energy. So what is the reference angle that we choose? The reference angle that we choose is 90 degrees or pi by 2 radians. And here, because cos pi by 2 is 0, okay, P dot E will be 0 or negative P dot E. So it turns out 0. Okay, so this is where the electric potential energy is assumed to be 0, and with this we can calculate electric potential energy at any other angle theta by negative P bar dot E bar. Okay, negative P bar dot E bar. But the main formula is this. Okay, the main formula is this. That is for electric dipole. Okay. Now in your book there are some theory topics associated with electrostatics of conductors and dielectrics. I will not cover them because there is no mathematics as such involved there. There is mathematics there, but not as a part of your syllabus, so I will not talk about that, but I will just be talking about one vector quantity called electric polarization P bar. Okay, electric polarization P bar, which is analogous to magnetization. Okay, which is analogous to magnetization. If you remember what is magnetization, M bar, it is what? It is magnetic moment per unit volume. Just like that, we have polarization P bar, which is electric moment or electric dipole moment per unit volume. Okay, and it is related to epsilon naught, that's permittivity of free space, and what is this? This is electric susceptibility. Okay, we have magnetic susceptibility here. Well, I don't think any sum will come from on this particular formula, but please remember that polarization inside a dielectric and electric field inside, they are related to each other. Or if you place a dielectric in an external electric field E bar, then it gets polarized. Actually, what happens in polarization is the immobile charge carriers. Okay, the immobile charge carriers slightly shift. Okay, if it had been a conductor, then the charge carriers would have started flowing. Okay, and that would have constituted an electric current, but in this case the charges move by very small margins. Okay, so that gives rise to gives rise to another electric field, and that actually acts in a direction opposite to the externally applied field, and that is the reason why capacitance of a capacitor increases when you place a dielectric inside. Okay, we'll come to that, but just remember this formula, polarization. Okay, it's a quantity by the way. Okay, it's a vector quantity, P bar. Okay, at last, capacitors. Okay, one quick message karo there to my next class students. Okay, capacitors. A brief description. What is the definition of a capacitor? Any two conductors, okay, any two conductors separated by An insulator is what we call a capacitor. There are various configurations, but no matter what the configuration is, the two conductors are often called as plates. Okay, because the most common capacitor that we use for our analysis is a parallel plate capacitor which has two plates. This is the symbol, and even for circuit diagrams we use the same symbol, okay, for capacitor. Okay, what is the job of a capacitor? Can anybody tell me what is the job of a capacitor?
Withhold and release current,
Not current, energy.
energy.
Yes. So a capacitor is an energy reservoir. Okay, it is an energy reservoir which can deliver the energy at very high rates, unlike a battery. That's why for flashes we use capacitors. Okay, we want the energy to be delivered within a very short span of time, so we use a capacitor there. Okay, the important quantity associated with any capacitor is its capacitance, and it can be proved, and we prove it for parallel plate capacitor, that capacitance does not depend on the potential difference. Okay, the capacitance C, okay, is actually the constant of proportionality between the charge, net charge on any one plate of capacitor divided by the potential difference. And we often say that it is Q by V, but by V we actually mean the potential difference. That's what I was telling you here at the beginning of our lecture. We say delta U equal to, okay, well, we say delta U is equal to Q delta V, but we often write it as U. Okay, yeah, for capacitors it is actually potential difference between the plates, but we write it as V. Okay, fine. Yes, okay, so C is equal to Q by V. What is the net charge on a capacitor? Net charge is always 0, because when a capacitor charges, we say that the capacitor is charging, and it is actually redistribution of charges. So the plates or the conductors are electrically neutral initially. When we charge the capacitor, okay, we actually redistribute the charges. So one plate has a net positive charge and the other plate has an equal amount of negative charge. So the net charge due to additivity on the capacitor is always 0. Okay, and the capacitance is actually a geometrical property. It depends on the geometry and the type of material that exists between them. The capacitance C is given by epsilon A by D. Okay, if it is vacuum, एक minute. If it is vacuum, then this is epsilon naught for vacuum, and for other media, okay, for other media it is epsilon naught into kappa, where kappa is the dielectric constant. Okay, for vacuum it is 1, for air is approximately equal to 1 but slightly greater than 1, and for other substances like water, dielectric constant is 80. And there is a table given, I guess, in your book, and even in our notes there is a table for dielectric constants. Not mandatory to remember dielectric constant values, okay, but just remember that they always increase the capacitance of a capacitor. Okay, then we also had discussed two more configurations of a capacitor. If you have capacitor in the form of a cylinder, so there will be a circular cylindrical conductor here and another cylindrical conductor here, and suppose this continues for a length of L. Okay, suppose this continues for a length of L. Suppose the inner radius is A and the outer radius is B, then the capacitance is 2 pi epsilon naught capital L, divided by the natural log of B by A, or ln B minus ln A. And if the capacitance is a sphere, like a shell, with inner and outer radii respectively B and A. Then the capacitance is given as 4 pi epsilon naught AB upon B minus A. Recommended to memorize these formulae. Okay, if they ask you suddenly to solve a sum on that, okay, it's recommended that you just remember the formula. Okay, next part. Capacitor combinations. When you connect the capacitors in parallel, okay, when you connect the capacitors in parallel, the potential difference across the plates is the same. Okay, the potential difference across the plates is the same. So the equivalent capacitance here is found out by adding the individual capacitances. Okay, you can remember it by using the par V in parallel combination. The individual capacitors as well as their equivalent, they have the same potential difference across the plates. Now what happens if you connect the capacitors in series? The same net charge exists on any plate, okay, of any capacitor if you connect them in series. Okay, because in electrostatic situations no current flows, right? So if it is 2 plus here, then 2 minus here. Okay, then therefore 2 plus here, 2 minus here, therefore 2 plus here and 2 minus here. The same charge. So in order to find this, we must use the formula 1 upon C1 plus 1 upon C2. If there are 3 of them, then 1 upon C3, and then you take the reciprocal of that. Okay, clear? So here lakshat theva. Let's now move on to the last part. The last part is energy stored in the capacitor. What kind of energy is this? This energy is the electrical potential energy. Okay, electrical potential energy. Why do we need this electrical potential energy first of all? Okay, for this, visualize the process of charging. Initially the plates are electrically neutral, and let's say an electron leaves this plate. It is going to acquire a positive charge, okay, of 1 unit, 1 quantum, and therefore this plate is going to attract the charge, the electron, and we are actually pulling it. So there exists potential energy. We need energy to that, right? We supply it to this, but it is a conservative field, conservative force, okay, Coulomb force. So the work done by the external force, which is in this case the external agent is the battery, the capacitor is charged, and then that energy is stored in the form of electrical potential energy. There are multiple formulae available. Half CV squared is the most preferred one, but the other two can also be obtained by using the formula C is equal to Q pi. Okay, so you remember all of that. Now, I just want to remind you that we can also talk about energy density. Okay, what is energy density? Energy density is given by the energy E, or okay, let me say U, divided by the volume of the space occupied between the plates, this space. Okay, if you calculate it for a parallel plate capacitor, in the textbook they say it also works for any other configuration. It is 1 by 2 epsilon naught E squared. Okay, if you remember, for an inductor of inductance L, it also has energy density. Okay, that energy density is given by 1 by 2 mu naught P squared. So these expressions resemble each other. This is in energy density for an inductor which has magnetic field inside it, and this is for a capacitor. Okay, if you go back and look at the chapter on electromagnetic induction and AC circuits, you'll understand what I'm talking about. Okay, so that completes our revision of second chapter, electric potential and capacitance. You can start solving the numericals and go through the derivations. If you have any doubts, you can ask me anytime.